Good morning, friends. बंद करके फ्लाइट मोड में. Today we are going to study temperature stresses in composite bars. So the temperature stresses in composite bars means yes, means bars in series or bars in parallel. Series means what? If suppose this is one end is fixed and this is the material. Suppose this material is steel material and this material is copper material. So such type of the arrangement are called as shaft in series. Shaft in series and shaft in parallels. This is in parallel. In parallel means suppose this is a one pipe and this is another pipe. And if this is enclosed and this is fixed, and if we are rising above the temperatures, means this is in the shaft in series and this is in the shaft in series and this is shaft in parallel, or this is called bars in series or bar in parallels. Now for such conditions, if due to rise in temperature, both material try to expand. So this expand alpha S, T S and LS. Suppose this length is and this is copper and this is copper TC and this is LC. So this TS equal to TC, rise in temperature. So this is the rise in temperature delta T. So alpha S T L and this is alpha T LC. Now this expansion is prevented. So yes, this is expand, try to expand. Next, it's a expansion prevented means because of the expansion prevented, both are fixed conditions. So that's why the structure means yes, reactions because of this force reactions produced, and this prevented means because this is the compressive stress and this is the compressive stress. So that's why we can write this is delta LS plus delta LC. So this is delta LS equal to P into LS divided by area multiplied by Young's modulus plus. Similarly here this is LC. Now this is AC and this is EC. So that's why here in this case, this is shaft is parallel, so we will see this is in afterwards. So first we will see shaft in series. So because of this, now here's expansion of shaft or bars equal to contraction of shaft in contractions of the shaft or bars. So that's why we can write this is alpha S T L S alpha C T L C equal to this is P L S A S E S P L C A C E C. Equate this, and this is nothing but stress. So here's everything is given. This is the alpha S is the coefficient above the expansions of the steels. This T is the rise above the temperature, length above the steel, and this is alpha C, coefficient above the coppers. T is rise above the temperatures, LC, and here's this is P divided by AS. So the P, what will be the force actings that is given according to that. So this PS LS and this PC divided by AC that you can calculate. So this is the condition. Try to understand this. So this is try to expand. Means this is the expansion for the steel materials. This is the expansions above the copper material. So both are expansions prevented. So this because expansion prevented. So this is not allow this pre-expansions, and this is equal to expansions prevented. So both should be equate. So this is the final equations. So note down first problem is a steel rod (750 mm) long has a cross sectional area (200 mm squares) over 300 mm of its length and 1800 mm squares over the remaining 450 mm at a temperature of 10 degree centigrade. the rod fits exactly between unyielding walls at its two ends. Calculate the reactions. The reactions at fixed support and maximum stress and maximum stress at 40 degree centigrade. Take E equal to (200 gigapascal) and alpha equal to 12 into 10 to the power minus 6 per degree centigrade. So in these problems, so this is not this is the shaft in series, but this is not composite material, because same in this case material is same, because this is steel. So this is 200 mm squares and this is 1800 mm squares. This length 300 mm and this is 450. This is fixed. Rise in temperatures, T equal to 40 minus 10 equal to 30 degrees centigrade. All right. So this is both ends are fixed ends. So that's why here we can consider this is the reactions. Supports means this is P. So assume P is the reactions at the supports, because this is due to rise above the temperatures. So that's why here's free expansion equal to expansion prevented. So this free expansions alpha into T, because this is the same material, so alpha T, and this is L1 plus L2, because this is I taken common. Now this is P1 or this is P LS, this is L1, this is A1, this is E1, P, or otherwise this is because same material, P, L2, A2, and this is E. So that's why, or otherwise this is, I consider alpha 1 T1 L1 plus alpha 2 T2 L2. Now this alpha T common, L1 plus L2, and here's this is equal to P divided by E, otherwise we can write this, and here's L1 A1 L2 E2. Same equations I am rewriting as alpha T L1 plus L2 equal to P into divided by E, L1 A1 L2 E2. Now alpha, this is given 12 into 10 to the power minus 6, rise of temperatures 30 degree, L1 300, this is 450, P that is to be calculated, this is 200 multiplied by 10 to the power 5, L1 300, A1 200, L2 450 divided by E2 1800. Alright. Now only one unknown, that is the P. So that's why you can calculate now P equal to. So this same equations can we write 1.2 into 10 to the power minus 5 30 into this is 750 equal to P. This is 1800. So that's why this is 9 plus this is 450 by taking LCMs. So this is 9 multiplied by 9. So this will get cancelled, and this is 1.2 into 30, or this is 36 multiplied by 750 multiplied by 200s equal to P in brackets 1800, this is 2700 plus 450, or otherwise P equal to divided by so P equal to 36 into 750 into 200 into 1800 divided by 3150. Oh shit. So here, so I consider this is 10 to the power 5. So that's why I am getting wrong answer. This is 10 to the power 3. 10 to the power 3 means this is 2 into, we can write 2 into 10 to the power 5. So this is 20, right? So this is equal to P equal to, this is support reactions, maximum stress equal to, now stress equal to, so this is P divided by A1 divided by A2. So this is maximum stress divided by 200. Actually both stresses are composite stress. So this is the maximum stress. So try to understand these problems. So maximum stress equal to megapascal, and this is compressive. So I think you better understand this problem. So that's why today we will see the next problems. So in these problems, both materials are same material. Now we will see when the material is different. Composite bars shown in figure, if the temperatures above the system, if the temperature of the system is raised by 60 degrees centigrade, calculate the stresses developed in the three parts. Take PS equal to 100 gigapascal, alpha C 16 into diameter of copper 60 mm. ES 80 gigapascal, alpha is 20 into diameter of the steel 85 mm. Now this is for aluminum material. This is for steel 200 gigapascal. This is alpha S 12 into 10 to the power minus 6 and ds equal to 60 mm. So first figure, this is copper, this is aluminium, and this is steel. Now, as per our conditions, so this is temperature 60 degrees centigrade raised by. So T equal to 60 degrees centigrade. So that's why here we can write expansion of material equal to expansion expansions prevented. So that's why here's this copper material alpha C T L S alpha A T L A plus alpha S T L S equal to, now suppose this reactions is the P, so P L C divided by AC, EC, PA, so the same ELA, AA, EA, steel. So here's first we'll calculate AC, AA and AES. So this is pi by 4, 60 squares, pi by 4, 85 squares, pi by 4, that is again 60 squares. So we'll calculate this in terms of pi. Right. So now can I write? So as per the given, so by taking 10 to the power minus 6 common, 10 to the power minus 6, now alpha C, this is 16, directly I am taking commons, temperatures 60 degrees centigrade. Now what is in the bracket? This is 16 multiplied by LC 250 right, plus this is 20 into 300 plus 12 into length 250, this is equal to, now by taking commons, P, and what is in the brackets? Now length 250 divided by area 900 pi, and this by taking common 10 to the power 3, so remaining this is 100 plus this is 300, 1806 pi multiplied by this 80 plus again 250 divided by area 900 pi multiplied by this is 200, bracket closed. So try to understand briefly. I written that. So that's why this is 10 to the power minus 6, this 10 to the power 3. So we'll solve this. $12 into 250, 3000. So we'll solve separately this, all terms separately. Otherwise complications increase. 250 divided by 900 by taken commons. This is pi. What is remaining? 0.0277 plus so this 10 to the power 6, 10 to the power 6 will get cancelled, and P equal to so this is equal to 655 newtons. I will check these answers. This terms is missing. So that's why this is 393 Newton. Otherwise 393 kilonewton. 0.4 kilonewton. So what is to be calculated? Calculate the stresses developed in each materials. So that's why in copper equal to in aluminum and in steel. This is equal to same divided by area equal to this area equal to 900 pi and this is same. So I think in copper and steels more stress induced. One 39 megapascal compressive. Here also same compressive, and here's $69.51 megapascals. So this is your expected answers. So this is today's second problem. That's why we'll see next problems. If the temperatures above the assembly as shown in figure is uniformly raised by through 40 degrees centigrade, calculate the stress in each portion if the supports do not yield. If the supports yields by take 200 gigapascal alpha s 12 into 10 to the power minus 6 EC 100 gigapascal and this is 16 per degree centigrade. Yes, figure given because we require figure. So yes, if the temperature stresses, if the temperature increases, compressive stress induce in both material. So that's why here's this free expansions. So yes, total expansions prevented divided by means equal to total contractions. Due to reaction P, right? So this expansion is prevented alpha S T L S alpha C T L C equal to this is P L S A S E S P L C A C and this is E C. Now rise above the temperatures 40 degrees centigrade. So I directly taking commons 60 into 10 to the power minus 6. Now alpha S, this is 12, length 400. So length we taken. So here three terms. This is one term, this is second, this is third, right. Next 16 multiplied by 300. Here's I only taken commons P divided by 1000. And what is remaining? LS, AS, and this AS equal to what is 200. This is 100. So that's why we will simplify this right hand side terms. 16 multiplied by 300 plus 200 this is 0.576 multiplied by 1000. So this is 576 equal to P in bracket. Now this is 400. So AS, this is pi by 4, 30 square multiplied by 200 plus this is 300 pi by 4, that is 20 square multiplied by 100. So that's why this is 576. Now by taking P into 400 multiplied by 4, 30 square, 200 plus 300, 20 squares into 100. And this is by taking P common. So this is simplified form. Right? So that's why so once again I will check this. So I here consider this is rise above the temperatures instead of the 40 degrees centigrade, 60 degrees centigrade. Otherwise, we will consider this is 40 as it is. Make corrections. So that's why this is 384 divided by so right, this is Newton. P equal to. So this is for first conditions if the supports do not yield. Calculate the stresses. So stresses equal to sigma S equal to P divided by area of cross sections pi multiplied by 4. This is 900 and this is for steel 31028 divided multiplied by pi. This is 400. This is 31028 multiplied by 4 divided by pi divided by 900. This is equal to 43.89 megapascal, and this is 31028 multiplied by 4 divided by pi divided by 400. So this is 98.76 megapascal. So this is first. So second bit, if the supports yield by 0.1 mm. So here, Miss, what is meaning of this? Alpha S TLS plus alpha C TLC minus. So yes, this is first is the if the supports yield, if the supports do not yield, and here's this yield means here's we have to add only this distance given, that is 0.15 mm, and rest of the things by keeping same as it is. AS, ES, AC, AC. So solve these equations, you will get answers. Sigma S equal to 26.74 and sigma C 60.17 megapascal. So due to limitations of the times, I could not solve these equations. So if you solve these equations, you will get these answers. So these are the problems related with the shaft in series or composite bars in series. So in the next class, we will see when the bars, composite bars in the parallels. So that type of the 2-3 problems we will see. So after that, we can see derivations and problems related with the derivations. So that's why today I stop here, and we will continue remaining portions in the of the temperature stresses in the next class. Thank you.